All right. So let's look at the following result, namely that if you have two subsets in universe U, if A and B are disjoint, then if A and B are disjoint, then if A and B are disjoint, then what? A intersection B is empty. All right. Of course, there's nothing to really. That is the definition of being disjoint. Okay. Disjoint means they have nothing in common. All right. Now we have the following theorem. Let's try to prove this theorem. Theorem two: if A and B are in universe U, then A and B are disjoint if and only if A union B is A delta B. Okay. So first of all, we should start by thinking. So we should say, okay, what is given to us? That we can say, okay, A and B are disjoint. That means what? So proof of theorem two. Theorem two. Let me write down the proof. Okay. So all the theorems always are accompanied by the proof. Okay. The solution to the theorem is called proof. All right. Now, so let's see. What is A delta B? Is A union B minus A intersection. Do you agree? Yeah. Now, A delta B. So A intersection. So A and B are disjoint. That means what? A and B disjoint. Imply what? A intersection B is what? So from here we get what? Here we get A minus B. Sorry, A delta B is going to be A union B minus an empty. Yeah. All right. And that is same as what? A. It's not a priori obvious to me that A minus, so we need to have this statement, right? A minus empty set is what? Okay. That should be clear. We can prove that if we need be. Okay. Now, the following statements are equivalent. Equivalent means what? These are same statements. Yeah. Generally, when you have some state, like, some people have, like, sometimes we have a, what do you say? Sometimes we have a different definition for the same thing, right? The reason why we have different definition for same thing, because sometimes it happens that there are a bunch of statements which are equivalent. Yeah. So if I have A is subset of B, if I want, I can replace that by A union B is B. Or I can replace that by what? A intersection B is A. Yeah. Or I can replace that by what? Complement of B is a subset of complement. Okay. So few things we can prove quite easily, actually. So let me just do some of the proof. Okay. So generally, when you want to show that four statements are equivalent, the ideal situation is you prove that A implies B. But if you want to prove that it's equivalent, you also have to prove B implies A, right? Do you agree? Isn't it? Yeah. Then only those two statements are equivalent, right? So a shortcut way of proving that all these statements are equivalent is you say A implies B, B implies C, C implies D, and D implies A. When you do this, you actually have proven what? All these statements are equivalent. That is an easy way of proving what? If there are many statements and you want to prove that every one of those statements are equivalent. Otherwise, imagine you have to prove A is same as B, then you have to prove what? A implies B, and then you want to prove that B implies A, therefore A statement is equivalent to B, right? That's a lot of work. So what you do is, if you have four statements you want to prove, you can say A implies B, B implies C, C implies A, C implies D, and then D implies A. So all these statements then become equivalent. Okay? Yeah. All right. Let me prove some of them, the low-hanging fruits, because I want to talk further. You can do this proof at home. But let's say A implies D. Let's just see this. This is pretty straightforward, huh? How can I do that? So we have what? If X belongs to A, this implies what? X belongs to D. Yeah. Now, if I use the contrapositive of this statement, right? Contrapositive of this statement is true, right? So what do I get? Negative of X implies B. Sorry, negative of X belongs to B implies negative of X belongs to. You agree with that? Yeah. What is negative of X belongs to B? Is X does not belongs to B implies what? X does not belongs to A. Yeah. So what does it mean? It means nothing really. Yeah, we haven't proved that. No, I mean, it doesn't mean anything really. X does not belongs to B. Okay, so question is, if X belongs to A implies X belongs to B, and then, okay, yeah, no, we are there. No, sorry. Premature. Now, X does not belongs to B. What does it mean in terms of complement? That means X belongs to B complement, isn't it? If X does not belongs to B, then it belongs to the complement. This means what? And here we get what? X belongs to A complement. So we have shown that B complement is a subset of A. Yeah, does that make sense here? Yeah. So this is how you can prove all these statements are equivalent. I want to move further. Okay, we cannot prove all the theorems in this, but it would be nice if you can basically go about proving all this. Okay, and if you get stuck at this, maybe we should talk about this in the next class or in the office hour, which is just before the class. Okay. The reason why I want to move further is because I want to talk about laws of set theory. Okay, so now we have few more laws. So like you had laws of logic, we have laws of set theory. Okay, so the idea is, let me write down few of them. So I take A, complement is basically what? All right. So again, you should think about this as complement being basically a negative statement. All right. So suppose X belongs to A. Yeah. What is the negative of this statement? And what is the negative of that statement? That is same as X belongs to A. Yeah. That's one way of looking at it. You can look at this proof also from Venn diagram perspective. All right. But that's your choice. Then we have De Morgan's law. Right? Immediate, same as De Morgan's law of logic. We have what? If you take A union B complement, that is same as A complement intersection B complement. Okay? You can again see this from Venn diagram perspective, or you can do it from logical perspective. Yeah. Let's see. Let's try to see proof of one of them, right? Otherwise, it will be, everything is in the air. So let's see. What proof would you prefer? So if you look at the Venn diagram perspective, let's look at that. You have set A, you have set B. A union B is this set, right? The whole thing. So A union B complement is going to be everything outside. Yeah. This is my A union B, the whole complement. Okay. Now let's look at the same thing from the perspective from the right hand side, right? So this is my left hand side, and let's look at right hand side. So A complement is what? Is basically everything outside A. Okay. Yeah. If you like, maybe if you want, you can color it, Now that is my A complement, right? What is my B complement? Outside B, right? So let's say everything outside B. Let's try to draw it. Should I use this color pen? Okay. Everything outside B will be outside B. Oh, you can't see this? Okay. 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 I'll do that next time. Yeah. So this part should not be common. Okay. Yeah. Okay. Well, too sensitive. Okay. So I wanted to draw basically. So first I drew A complement, which was basically the red color. And now I'm drawing the B complement, which is basically everything outside B, right? So this should not be there. So B complement is everything outside B. Okay. So now, if you look at this, whatever is having checks, crossings, is what? Sorry, where did you go? Card. whatever is in checks matches for basically both of them. So essentially you have what? You have A union B complement is same as A complement intersection B. All right. So this is De Morgan's law. Let's try to prove it from logic perspective. All right. So let X belong to A union B complement. All right. So this would mean what? X does not belongs to A union. Yeah. This means what? This means X does not belongs to A. Now note, generally we would have OR, right? But here we would say X does not belongs to A and X does not belongs to B. Right? This would mean what? X does not belongs to A. So now we can replace this by what? X belongs to A complement and X belongs to B complement. This means what? X belongs to A complement intersection B. Right? There's nothing really special about one direction. So we can have if and only if. This case as well. Yeah. So this is the De Morgan's law. All right. So similarly, if you have union, you take complement, you get intersection of the complements, and vice versa. If you take basically intersection complement, then it's going to be union of the complements. Okay. Commutative law holds as well. A union B is same as B union A, or A intersection B is same as B intersection A. Associative law. Now, again, here, if you have same operation of union, whether you do, so you have three sets, A, B, and C. If you want to take union of these three sets, it doesn't matter whether you take this, as a union, or you take basically A union B, union C. So these two are same. However, if you have union and intersection, then there will be a distributive property. It's like and or, right? Union is like or, intersection is like and. Okay. So we have what? If you have A union B intersection C, this is same as A intersection C. See, I'm distributing it. Union B intersection C. This is a distributive property. All right. Okay. And then there are same thing like identity, inverse, and all those things. We'll see when we are looking at one of the problems. Okay. Now, sometimes we can basically think about this as a what do you say? As basically as membership table. Okay, let's try to do an example. All right. So this is what we want to see. Let's see. A union B intersection C. Then I take a bar of this. Union B bar. The whole bar is equal to B intersection C. All right. So we want to show that these two statements are equivalent. Let's try to do it in two ways. One way is using the laws of set now, which will be provided to you during the exam. The law of set theory. That's one way. Another way would be basically using the membership table. Okay. So let's do that both ways. Okay. So now, here I can think about this as, so it doesn't matter. You want to go from bottom to top, from inside to out, or outside to inside. It doesn't matter which way you want to go. Now, can you think about this as one unit and this is another unit, right? And you're taking union of those and you're taking complement. Yeah. So if De Morgan's law kicks in, I should say De Morgan's. Again, De Morgan was the name of a mathematician, by the way. So it's going to be what? A union B intersection C bar bar. And the union becomes what? Intersection B bar bar. Do you agree with this? Yeah. This is two blocks, right? This is one block here. You can think about this as one block. And the other block is this one, right? So you have block one, union block two, complement is what? Block one, complement, intersection, block two, complement. Yeah, is that okay? Yeah. Now, bar and bar cancel out, right? So we can basically say bar is same as set. So that's why I chose to go this way, because I could see that simplification is happening. You could do other way around as well, okay? As long as you keep consistently applying the laws of set theory and you are seeing that there is a simplification happening, you are good to go. Yeah, it will work out. It will simplify itself slowly over a period of time. So let's see. So bar, so I get what? So I get here A union B intersection C intersection B, yeah, is equal to, yeah, this is what we get, right? And again, I will say double complement. Now we don't need to distribute yet. I mean, I can see that we can distribute, but if I distribute, you see on this side, when I'm looking at this problem, I see if I distribute, then I will have A intersection C union B intersection C. And then I have again intersection with B, right? So what I'm going to do is I'm going to switch B and C, because my hope is maybe it will work out, maybe not. My hope is that A union B intersection B simplifies somehow. So again, I'm going to simplify this as A union B intersection B intersection C. Yeah, you can change them as long as the operations are same, right? Here we have intersection, the other one is intersection. If they are not intersection, then we are in trouble. If they are not same, then we are in trouble. Then we need proper brackets around things. We can't write it like that. Okay. So now we have what? A union B. So again, let me just erase that. I don't want to give an impression. So now I have A union B intersection B. Okay. So now either we have some laws of set theory related to this, or we try to distribute it now. Let's see. Is there any laws of set theory related to this? You have A intersection B union C. Well, there's a distributive law. If the absorption law will work, A union A intersection B is A. Let's see. Is it working here? A. So, or you have A intersection. Let's see which one will apply. You have inside, you have union, right? And you're intersecting with A. Then you get back what? A. So here we have A union B, and we are intersecting with what? B. So we'll get what? B. Again, what is that law which basically simplified it? Absorption. Absorption. Law of observation, absorption, basically, which is your RHS. Okay, makes sense? Yeah. Now, another way would be, which is going to be slightly interesting or rather painful, to be honest, is basically using a membership table. Okay, so let's do one problem based on membership table because it's a good idea to go about it. Okay, so let's see. So I have A, let me just write it down here. I have, what do I want to prove? A union B intersection C bar union B bar, the whole bar is equal to B intersection C. This is what I want to prove, right? Let's start with the membership table. So now how many variables are there? How many sets are there? There are 3 sets. So there will be, it's like having 3 variables. Okay. So we will have basically what? We will have 2 to the power 3, which is 8. So let's see. So we have A, B, C. You write 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay. Now, what is the idea behind this? See, when you're doing this, you are saying, let me take all the possibilities. X is in A, not in B, maybe in C, right? Or X is, when you look at 0, 0, 0, that means you're taking something which is not in any of those sets. If I look at 1, 0, 1, that means I'm taking an element X, which is in A and C. So membership table, what it does is it lists out all the possibilities. And for every of those possibilities, you're working out the solution. Does that make sense to you? This is similar to logic as well, right? In logic also, you had 2 ways of doing things. One was using the membership, one was using the true and false table. There also you are investigating all possibilities for statements. Yeah, or you can have laws of logic to do the. So generally, if depending on how complicated the statement is, if the statement is complicated, but the number of variables is small, membership table might be. if the statement is large, yeah, sorry, if the number of variables is large, then I think it makes more sense to basically do what? Do reduction, laws of set theory. Okay. All right, so now we have to construct painfully everything. Huh? So A union B. So note that union behaves like OR. Okay. And then we have what? A union B. So let's see, what is A union B again? So A union B is going to be when you have OR, right? So we have this here, we'll have 1. Here we have 1. Here we have 1, 1, 1, 1, 0, 0. Right? You agree with that? Okay. Now we have what? B complement. So B complement. Let's use the same color pen. B complement. B complement is exactly negative of it, right? So it's gonna be B complement is same as negative, right? So we have 0, 0, 1, 1, 0, 0, 1, 1. Okay. Now I need basically oh, I should have intersected this with C, right? So I need now, I can do it here, A union B intersection with C, right? So again, this is gonna be an AND operator for A union B. So I'm gonna compute AND of this, right? And bring it here. Let's do the AND of these guys. So AND basically is 1, 0, 1, 0, 1, 0, 0. Okay, perfect. All right. Now we have to do what? Complement of this. So it's gonna be A union B intersection C complement. So it's gonna be again flipping, right? So 0, 1, 0, 1, 0, 1, 1, 1. Okay. Now we have to do what? We have to do union with union of this with what? Let me just write it down. Union with sorry, I'm looking at union with B bar, right? So again, I'm looking at OR, right? So I'm doing basically OR of this. So I'm doing OR of these guys, right? And putting it here. Do you agree? Yeah. So let's see. So when I compute OR of this again, so OR of these two. So 0, 1, 1, 1, 0, 1, 1. Okay. All right. So now I need to do basically bar of this whole thing. Yeah. So this whole thing bar. So A union B intersection C bar union B bar bar. Okay. So bar of this, right? So negative of this guy. So we have what? Yeah. So we have 1, then we have 0, 0, 0, 1, 0, 0, 0. Okay. We better have not made any mistake. Hope so. Now let's see B intersection C. That means AND of these two, right? So we have B intersection C. So AND of this. So let's just check. So first one is going to be 1. And then we have 0, 0, 0, right? Yeah. So 0, 0, 0. And then we have 1. And then we have 0, 0, 0. There you go. All right. Painful process, but again, I'm not saying I'm a true mathematician, but we want to basically, I mean, if you're not brave enough, then there's no point of doing math, right? You have to basically, like, if you want to prove something, you have to go all in. You can't be like, oh, half of it I'll do it, and then no, you have to go basically all in. Okay. Anyway, the point is that yeah, they are indeed equal. So this is how we do it by membership table. Okay. All right. So that's that. So and then similarly, same thing can be done by Venn diagram. But if the statement gets as complicated as this, coloring after some time is going to be really painful. So, Venn diagram will have simpler statements. You try to prove simpler statements using Venn diagram. Or you can do it by sequence of Venn diagram. You can't just do it on all in one. Okay. Now comes a very interesting thing. Now comes the cardinality of union. Now this is a very powerful result. Okay. You can see this. I mean, yeah, we can keep talking about lectures and lectures about it. Okay. So this is principle of inclusion exclusion. So now, so idea is basically, first of all, let's take a look at a basic idea. I want to count what is A union B, size of A union B. Okay. I want to be able to relate it with size of A and size of B somehow. Okay. Let's draw a diagram and it will become clear to us. So let's say, suppose this is my set A, this is my set B. Okay. Now, what is size of A union B? So so A union B is this set, right? Do you agree? Now that is same as size of A, right? So size of A is going to be all of this plus size of B. Now, but when you're doing that, something you're counting two times. Yeah, you're counting the intersection two times, right? It is getting counted as A in A as well. It's getting counted in B as well. So if you're counting it two times, you wanted to only count it how many times? One time. So what we'll do is we'll subtract that. So this is the principle of inclusion exclusion. So if I have A union B, the size of A union B is going to be size of A plus size of B minus size of A intersection B. Is that okay? I mean, you can see it from a trivial example, but examples don't prove results, right? But let's see. You have set A is 1, 2, 3, 4, 5, and set B to be 2, 3, 5, 9, 4. Oh, let's just not have too much intersection otherwise. Okay. All right. Now, what is A union B? A union B as a set is going to be 1, 2, 3, 4, 5. I exhaust that. And then I see, okay, 2, 3 counted already. 5 is already counted. So now, right? So now, and what is, so let's count now. What is size of A union B? Is 1, 2, 3, 4, 5, 6. Right? What is size of, right? What is size of A? 5. Size of B is what? 4. What is A intersection B? As a set, it's going to be 2, 3, 5, right? The size of A intersection B is going to be 3. Yeah. Let's see. Does it fit the whole thing? So size of A union B is 6. Size of A plus size of B minus size of A intersection B is 5 plus 4 minus what? 3. The same as 6. So these two sizes match. All right. But again, this is not a proof. This is just one illustration. Yeah. You remember the example? I bring a bag to you with a lot of stones in it. I cannot just take out one stone and say, hey, stone is gold, so everything is gold, right? It could be crap as well. Yeah. So the idea is that when you want to prove it for everything, right? But this is a what do you say? Yeah. So this is the idea. Right? Now, what becomes interesting is, if you are interested, I mean, it's not part of the course. Inclusion exclusion with 3 or more sets. That is really interesting. There's a lot of interesting mathematics it leads to. For example, suppose think about a play where you have chairs and then people move around with the chairs. Suppose there are like say n people and n chairs, and people are moving. So everyone has their own chair. Suppose. Then you move them around. How many different ways you can make them sit so that nobody sits on their chair? That's an interesting problem. This can be solved using inclusion and exclusion. Anyway, so this is the principle of inclusion exclusion. Let's move ahead. All right. So the next theorem I want to talk about is the following result, which is saying that n plus 1 choose R is same as n choose R plus n choose R minus 1. Okay. So now, if you look at this result, well, if you just want to prove it by brute force, by algebra, it's easy. It's slightly, it's a bit of a work, but it's easy using algebra. Let's try to see by algebra and then try to come up with a nice combinatorial proof. Okay? So if you do by algebra, what do you have? What is n plus? So LHS is going to be, or let's start with RHS, okay? And we want to show RHS is same as LHS. How about that? Okay. So let's start with RHS. The reason for starting with RHS is because RHS is slightly more complicated than LHS. So if n choose r, what is the form? What is the formula? N factorial divided by n minus r factorial plus n factorial divided by r minus 1 factorial times n minus r plus 1 factor, right? N minus r minus 1 will become. Okay. Now, let's see. So what can we do here? So this is same as n factorial. Now, I'm going to, let's make some changes so that we can take a lot of chunk common. All right. So let's see, n factorial is common in all of them. So I will leave n factorial as n factorial. Okay. Then I'm going to take it common. Let's look at r factorial first. Okay. So what is r factorial here? And here we have r minus 1 factorial, right? So we can break that as what? R times r minus 1 factorial. Do you agree with that? Yeah. So that we can take r minus 1 factorial common. And then we have n minus r plus 1 factorial. And here we have n minus r factorial. Now I want to break it like this. So which one should I break? Do you agree that this can be broken now into n minus r plus 1 times n minus r factorial? Right? Because it's r plus 1. So you can go one down by subtracting 1 from it, right? Yeah. Or if you don't like, you can say this is same as n plus 1 minus r. Huh? Like, addition is commutative, right? And then if you do this factorial, you can do n plus 1 minus r and then go one down, which is going to be n plus 1 minus r minus 1 factorial. So this 1 and 1 cancel out, right? That's how you go down the factorial line. Okay. Now, why did we do that? Because our goal is to take whatever we can take common and hope that things inside simplify. That's one way of going about it. So let's see, what do I get here? I can take n factorial common. I'm going to take r minus 1 factorial common. I'm going to take n minus r factorial common. Okay, let's see what remains. First one, we'll have 1 upon r left. And second one, we have what? 1 upon n r plus 1. Okay, now we need to simplify this. Let's cross multiply and see if we can make it look like this guy. Huh? So we need n plus 1 on the top. So let's see if things simplify in our favor or not. We'll try to simplify it as much as we can, hoping that it simplifies. So we have what? N minus r plus 1 plus r divided by r times n minus r plus 1. Okay. So now what will happen? This r and this r will cancel. So what do we have on the top? We have n factorial times n plus 1 on top. On bottom, we have what? We can combine now this r and r minus 1. So let's write them together. We'll combine them in the next step. And here also, we can write it as n minus r plus 1 is same as n plus 1 minus r. Do you agree? Times what? N minus r. Okay. Now combine. So this is going to be, this will combine to give you what? N plus 1 factorial on the top. This will combine to give me what? R factorial. And here we'll have what? N plus 1 minus r. Is that okay? Because you have n factorial times n plus 1. That becomes n plus 1 factorial, no? Yeah, you combine them together, right? So now, think about this as box. This is, so we have what? We have box choose r. Isn't it? This is same as n plus 1 factorial. This is same as what? N plus 1 factorial. Sorry, this is going to be same as what? N plus 1 choose r. Does that make sense? So if anyone is not convinced, I can talk about it. Anyone? So this is an algebraic proof. As you can see, no doubt it is painful. Yeah. But it is what it is. I mean, like, this is how things go. You try to prove it by some brute force method, it's going to be painful. Let's try to see a slightly nicer way of doing it. Okay. So now, I have n plus 1 element, and out of that, I'm going to choose R. All right. So now let's do the following. Let's take n plus 1 element. So A1, A2, dot, 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 AN. And I'm going to call the n plus 1 element as X. You will see that Y. Huh? You can call it AN plus 1 as well if you want, but then you'll have to be careful when you're, okay. So now, out of this set, I'm going to choose R element. So choose R element. Yeah. How many ways can I do that? N plus 1 choose R. Do you agree? Isn't it? Yeah. Out of n plus 1 element, I'm choosing R element. So it's going to be n plus 1 choose R. Okay. Now I'm going to break this process into two parts. The same, I'm going to look at the same choosing R element in two different ways. Yeah. Whether my X is chosen or X is not chosen. Yeah. I mean, I'm making an R element set. It is possible that X is there. It's possible that X is not there. Makes sense, right? Yeah. So let's look at the case when X is there. Yeah. So if X is there, then X is not bringing any uncertainty. Do you agree? Then essentially what you're doing is you're choosing what? So X is already there. So there's no point of choosing X. X is there. So out of n elements, how many elements are you choosing now? R minus 1. Do you agree? Because one element X is already chosen. So okay. Now, plus, suppose X is not chosen. Yeah. So how will we look at that? So if X is not chosen, you know that what? X is not there. So again, it's not going to participate in the choosing, right? So that means what? You're choosing out of these many elements. So it's going to be what? So this is a combinatorial way of looking at the same problem. I see you're all are toast pretty much. I mean, I can see your faces. Yeah. But you know what? I'm not going to stop. I want to discuss one last topic, which is really powerful. Okay. And here it goes. Okay. If you get this, it's fine. If you don't get this, we can repeat it next time. Okay. So now comes the idea of the binomial expansion. So I have, suppose I take 1 plus x squared. Yeah. Let me see what are the elements of x plus 1 squared. So do you agree that 2 choose 0? It is what? 2 choose 1 and then 2 choose 2. Do you agree? Yeah. You arrange them in a proper way. Huh? I mean, it's not randomly ordered. You have x squared, you have xy, and you have y squared. You want to choose the coefficient. The first one will go to the first one here. Second one will go to this one. Third one will go to this one, right? Now, I have x plus y to the power 3. Yeah. So if you recall, how does x to the power y plus 3 looks like? It's x cubed plus 3x square y. Note that the way powers of x are increasing and power of y increasing. 3xy square plus y cubed, isn't it? Now you see that this is same as 1, 2, 1. Yeah. And the way we construct for cube is we write 1, 1 on the top. We have add this and we add this. We get 1, 3. For the power 4, x plus y to the power 4, what do you do? Again, you do 1, 1, 4, 6, 4. Yeah. This is called Pascal's triangle. Yeah. Question is, why is this true? Yeah. So what do? We basically add it like this, huh? Or we add it like that. Let's say we add it like that as well. Okay. This is how we are constructing the Pascal's triangle. We take two things, add them, and put it in the center. All right. Now let's see the connection. So why the Pascal's triangle is true? What is this term here? Look at this term. It is going to be what? Let's write it down. So we have x cubed. Sorry, we are doing power 4, right? So we are starting with power 4 is the first one. So last one is y to the power 4. And the second last one is what? Y to the power 3 x. You agree? So what is the coefficient here? So if you start with n choose 0, x to the power 4 y, sorry, x to the power 4 y to the power 0. Then we have what? So 4 choose 0. Then we have 4 choose 1 x cube y to the power 1. Then we have 4 choose 2. Then we have what? 4 choose 2 x square y square, right? We are choosing powers of what? Y. Plus we have what? 4 choose 3 x what? Y cube. And then we have 4 choose 4 what? 4. Okay. All right. So now this is what? This coefficient is equal to what? 4 choose 3. Yeah. This is equal to. Now here, if you look at power 3, this is same as 3 choose 2. So this is basically same as 3 choose 2. And what is this element? This is same as what? 3 choose 3. Right. This is same as what? This is your n plus 1 choose 3. Or I can write it like that, just a second. So I can think about this as 3 plus 1 choose 3 is same as 3 choose what? 3 choose 2, which is 3 minus 1 plus 3 choose. So this result is actually same as the one we just now saw, which is this result here. Yeah. So this result, even though howsoever innocent looking it is, this is the whole basis of Pascal's triangle. This is a proof for Pascal's triangle, right? I mean, like, we have been using Pascal's triangle all this time without looking at the proof. This is a proof of how we can go to the next level by taking sum of these two and getting